All right, so let's get right into the UTAPWeLS developments. All right, so this year, like every year, we've been working on developments in 3 main lines. One of them is user friendliness and usability. We've been doing some updates in the track display, the mnemonics, the templates, the DLIS. I'll go into a little more detail in all these things. Very importantly, now we can handle arrays. Another line of development is general petrophysics. So now we have a general calculator. We'll go into a little more detail. The fluid model that we use, the simulations, and so on. Also, the inversion capabilities, like Carlos was mentioning, we have a much faster fast fluid flow simulator, and we have 2 brand new methods for log inversion and for joint inversion. We're going to have talks about those tomorrow, and we're going to have a demo about them today. So we're going to have full coverage of this part. Everything is developed in a Multiwell framework, like we've been doing for the past 4 years or so, and everything has scripting access. I know that scripting is something that only roughly 10% of the users do use, but those that do it, they get a lot more benefits than if you don't. So I also keep that in mind. All right, regarding the track display, we have, like pretty much every year, we've been improving it and modifying it. We have relocated the controls. Now they are in the bottom. That's where you would choose to zoom in, zoom out, select sections, and so on. We have a new mini module, you could say, called Quick Crossplots, where you just click there, select a section, and it's going to give you a crossplot of what you have there. You can modify the sources, so if you want to see something different, it's very easy. But by default, it's just going to make a crossplot of whatever you have in that plot. In that case, I have the resistivity log and an Earth model inverted for that. And you can see how the histograms are different. You can see how they relate to each other. And like I said, you can modify the sources to anything you want. Also, you have a concept we introduced last year that we've been using we've been integrating into the entire UTAPWeLS, is the MD selections, which is exactly that, just a selection of certain measured depths that you can visualize in different ways. This is, of course, one of the places where you would like to see that. So you can click there, draw a polygon, and select a certain set within that crossplot and see how that relates to something else. So once you make that selection, it will show also in the track display. You can also do those selections the other way around. You could make the selection within the track display and show it in the crossplot. So it's both directions. And of course, this is one of those things that, yeah, it's user interface, but it's not just using it. It's the petrophysics that you're going to be able to do are very different than if you don't have this analysis. Also, we've had the templates. We started using them a couple of years ago. We've been refining them. This is a template is just a view in the track display. We have a control up here where you say, OK, I want to see this setup. It could be just focus on the petrophysical parts. You could have the triple combo, anything. And you can just select another one. For example, Bruce made one for fluid flow. So you want to focus in certain fluid flow properties. Just select the other one, and very rapidly you can switch from one view to the other without having to close and open the well and so on. We've just simplified this part. We added a couple of buttons up here. It's easy to add a template. You can save a template in user preferences, which means that that template is going to be there for not just this project, but any other project and any other well that you may want to work with. And the last button is just to open the template manager. A word about templates. Sometimes it's confusing, but I think if we make it clear from the get-go, I hope it's clear for everyone. The way they work is each well has its own group of templates, so the number of views that you may have. And at the same time, we have some of them saved in the user preferences, the computer itself. By the way, you can share that with colleagues, and it's very easy to transfer them between computers. So you have 2 sets. And anytime you have a new well, it's always going to have all the templates from the user settings. And at the same time, you can save them there. If you modify something and you want to save it there, that's OK. But once you have it in the well, that's going to be independent from the one saved in the user preferences. So you can make any modification in that particular well without having to modify anything else in the other wells. If you think that that's useful for other wells, you can save it, and then it's going to stay there for any following wells. And if you already have a well open, you can just go back to the setting that was saved. Anyway, that window that explains that anytime if you get confused about it, if you click here in that question mark, it's going to show you what that explanation that hopefully makes it clear. And of course, this is very easy to understand. You just have the list of templates, whether it's saved in the user preferences or not, whether you want to save it or whether you want to retrieve it. So those things that I explained, everything is within this table. You can also duplicate a template. In many cases, you have a template that you want to keep, but you want to have a slight modification somewhere else. You click duplicate, you select which one you're going to duplicate, and click OK, you get it. Something else that we've improved regarding mnemonics is we have, well, regarding view, is we have expanded the definition of mnemonics. Before, it used to be just a set of curves that would be associated to a single mnemonic. So you would have, for example, this mnemonic gamma ray or GR would have a, well, the description is new, but it would have a unit class, a unit display, and it would have a set of curves. Now we've expanded that to have a visualization. So it would have a specific line, a specific color, specific scale, specific limits. We built this with a set of curves that was kindly provided by Winters Haldea. But if you have different standards, we can work with you. And if many companies are interested in just being able to upload it themselves, it's easy for us to just make it accessible through Excel. Or, of course, you can modify them. You can always add. You can always play with them. So this is a good start. And you can also just modify it in place. That's also very easy. Just to keep things standard everywhere. Another big improvement that we've had is we have now a DLIS reader that Bruce developed. We've had a DLIS reader forever, but it was very clunky, it was very slow, it was developed externally, and we didn't exactly know how it worked inside. And that's always a bad recipe, because if it's a black box, you don't know how to improve it, and we couldn't improve it. Now we can improve it. It's very fast, it only loads what needs to be loaded, so it's efficient. And very importantly, now you can load arrays. And he did it not in such a way that not only you can do that from DLIS, but you can also do it from LAS. At some point, you were able to generate arrays within UTAPWeLS, but you would have to do it manually. Now you don't have to do anything. You just say, hey, load this, it's an array, it'll do it by itself. And he did it not only for DLIS, but also for LAS 3.0. So we've expanded we had those options, but we really made it a lot more convenient, which is important. Of course, you can visualize any of the arrays. These are just a few examples. Very easy to do now. Also, well, this module went through some smaller improvements, but I'm also going to use it as an example of the Multiwell framework. Last year, we had many modules in the Multiwell framework, but not all of them. Now, every single module that we have within UTAPWeLS is with the Multiwell framework, which basically means that you have an option here to select the well that you're working with. You have a little option down there to select whether you want to expand those settings to other wells. You're going to have always these three buttons. Either in this case is detect, in other ones is run, and depending on what you're going to do, there's three actions always. In this case, whether you're going to detect boundaries only in this well, or if you want to do it in multiple. And the third one is that IOO is interval of operation, which tells you whether you want to work in a specific formation or the modeling interval or certain rock class, just what you're going to operate on. The one small improvement here, we have now layer thickness. If you want to see it after you've detected the boundaries, just for quality control, you can generate that histogram. We also added another method. This was developed by Ali Ekbali, one of his many contributions to UTAPWeLS, which is called the step function method, which works particularly well with noisy data. Another new, or rather than new, big step forward module is something that we call the general calculator. Before, we used to have a general calculator that would work only for curves, logs, but now, because it's UTAPWeLS, and the main reason why you use UTAPWeLS is because you want to develop an Earth model that is consistent. So instead of just working with logs, which you could do with any of the commercial softwares, we are including the possibility of using Earth model properties as part of your inputs or the outputs. As part of that, so this table just have the number of inputs. You define the inputs in these columns. You have a valid name down here. In this example, I'm just doing the Archie's equation using different n's. So I'm going to calculate water saturation using 1.9. Everything is Earth model, so you just specify what you're going to use in resistivity, porosity, and so on. And then the output, it could be any property from the Earth model, but something else that we did is now you can define your own Earth model properties. That's something that had always been a question in previous workshops and consortium meetings. And it sounds simple, but it was not that simple. Now we finally got it in there. So you can say, for example, you can just click in here and say add a property, and you just define what is the name of the property. So in this case, I'm just defining water saturation for 1.9 and for 2.1 n's. You decide the type. There's the type you would put in here, the units that you're going to use to visualize it. And you say, OK, for type, there's a help in the question here. In most cases, just use full. I don't want to overload you with data. Full is fine. And if you run it, you would get, well, you can run it, like I was saying, using Earth model, or you can use curves. So these are the results. If you, in the very right, is for 2.1 and for 1.9 using the curves, and this one over here is using the Earth model. And you can see the difference between the two of them. It's a little bit like a sensitivity analysis, but by layer. It's just one example. You could calculate anything you want here. Also, we have done some work regarding effective medium theory and models, in specific the fluid models. Now we have mixing models for multi-phase, which is relatively straightforward. We're using just breeze mixing, but it has important consequences. Now, if you have gas and fluid within the same layer, it's going to mix appropriately, not just using whatever equation that you would put for effective medium theory. It's going to mix them here to give you the elastic properties that would make more sense from a physics point of view, which is what we want, of course. Something else that we've done for fluids is we have now a density of fluids button here. There's a number of places where you're going to see this button that is going to show you the same thing. You see it from the palette. Any place where you are working with densities of fluids, you're going to have this pop up. And we have two options. We're giving you two options. They are saved in your computer in the user settings. So once you modify that option, everything you do is going to be using that option. The two options are using Peng-Robinson equation, which is what we've had forever, and the Batzel-Wang. Peng-Robinson is a really good equation. However, you need to have, well, it's really good, especially when you're around critical temperature or critical pressure. The problem is you need to know the critical pressure and the critical temperature, the eccentric factor, which is even more complicated to get, and the molecular mass. In most cases, people were saying, well, I don't have that, but I do have the density, or I have the gas gravity or the oil density, especially in cases where you're not exactly sure what is the chemistry of the oil that you're working with. So for that case, you use Batzel-Wang. Anyway, so both of them work. They give you pretty similar results, but the inputs are a lot easier to get for Batzel-Wang. We've done some improvements in the fluid component editor. We've made it a little easier. These are relatively small. We just added property groups, so it's a lot easier to see if you're, for example, if you're working with effective medium theory, you just see the things that are related to effective medium theory or any of them. Now in fluid flow simulations, the window doesn't look very different from what we had. It's actually the exact same window we've had for 5 years or something like that. But the use is going to be very different. Bruce took a deep dive into the code. This code is in Fortran. And he cleaned it up a lot. And, well, we added the Multiwell framework. And the big difference that you're going to see is that it's very, very fast now. If you remember, people that have been using this module for a while, the 1D simulations used to take under a minute, but a few seconds. Now, some of them are pretty much instantaneous. Of course, it's going to depend on the number of layers that you have. It's going to depend on how complex it is. I cannot tell you, OK, it's always going to take this much. But roughly speaking, it's down to a tenth or so that what it used to take. Also, for the 2D, it used to be 15 minutes or something like that. Now it's under a minute. And that's a big difference, because if it's 15 minutes, you can say, OK, I'm going to run it, go get coffee, come back. The second time, second coffee, OK, I don't need no more coffee. That's it. So you're probably going to run it 2-3 times. That's it. But if it's taking under a minute, you're going to be able, in that hour, you're going to run it 20, 30, 40 times. So you can test a lot more hypotheses, which is what this module is about. And you can see if you get a good match or so. So this was a big development. And also, the memory usage was improved. For heavy users, this was one of the complaints. If you use this module for a long time, at some point, the memory in your computer was going to start suffering. Now we made it only save things that are going to be actually relevant. Makes a big difference. It's a lot friendlier with your computer itself. And now regarding inversion, we developed 2 new methods. We're going to have talks. Gonzalez is going to give one. I'm going to give one. And we're going to have a demo to show you this. We've had a module to do separate inversion, which is basically if you have a property and you want to, if you see that the simulated log is not matching, you want to find an Earth model that, you want to modify the Earth model so that the simulated log matches. We've had that for a while. We've also had an option to calculate standard deviation. Now we've expanded this functionality so that we don't only calculate standard deviation or confidence intervals, but we have the full, a full statistics open probabilistic distribution. So any distribution can be the answer. Now we're going to have talks, so we're going to go into a little more detail in later tomorrow. And it's fast. You're going to see it takes a couple of minutes to get this done. And like I was saying, you can see confidence intervals. Right, and in visualization for confidence intervals, you can see them just as error bars. You can also see the standard deviation. In the first case was the standard deviation. The second case is the confidence interval. We also added a possibility to view the probabilities as heat map. So you can see here, of course, the yellow means higher probability, and you can see that these cases are less poignant. Over here, it's a little more, the difference is a little more stark. Anyway, it gives you an idea of how the probabilities really look like. And yeah, the visualization, interestingly enough, we've noticed that in some cases it's good to get rid of the line, so you can also get rid of that line, and it's another way of viewing things. We've also been working with a compositional joint inversion. This module, just in a few words, you have a set of input properties, which are physical properties related to logs that you would invert for in the module that I showed you previously. And then you want to turn those into petrophysical properties, meaning the composition. These are, well, the outputs that we call here. Mostly it's going to be porosity, water saturation, shale concentration, and the mineral composition and fluid composition. You're going to have, again, your inputs, and you're going to have the expected outputs here. Those expected outputs are going to have some prior probabilities that I'm going to talk about in the next slide. Notice that the outputs are by rock class. If you recall, in UTAPWeLS, a rock class is a set of parameters for certain modules that are associated to specific layers. Every layer has a rock class. So, for example, you can have a shaly rock class that is going to have all these modules, the Archie's equation and permeability equation, with the parameters that you would use for a more shaly layer. And if you have one that is more sandy, those parameters are going to be slightly different. And you would expect different mineral composition in those cases. Or if not the composition, at least the fractions would be different. So those priors are going to be different. What you expect is going to be different. Something else that is relevant in this development is that we enforce structural consistency, meaning that we can force the results to be dispersed, or to be laminar, or to be just respecting non-porosity, non-shale porosity, meaning that we make absolutely sure that the results are physically possible. That's the bare minimum that you should always have. But you can go a step forward and say, I know this is laminar, force it to be laminar. The priors, this is what they look like. For any of these outputs, you're going to have a prior that you're going to be able to modify. It's interactive. You can drag and drop things here to modify the standard deviation or the mean. You have a minimum and a maximum. You can guide yourself with histograms. You can overlay any data you may have. You may have core data. For example, this is for shale volume. You may have core data, or you may have done the interpretation in a separate well, but with the same information. If that was successful, you use that as your prior, and you can just you can have a Gaussian mix, so meaning you can have multiple Gaussians. What you really are going to use is the dotted black line in this case, which is just the addition of these two. Or if you see something like that, that's very separate. That's probably telling you you have two rock classes, so just use one for the one that is less shaly and one for the one that is not so shaly. You can restrict it a little more, something like this. And then once you run it, you're going to have something that we call the diagnostic plots, which is going to show you the properties that you're using as input. These are the solid blue lines, so gamma ray and so on. Those are the properties that you're assuming they are correct. And then it's going to show you in red the properties that you were able to produce with the outputs that were selected. So with a composition that was proposed as the right solution, you can calculate using UTNUPRO or SNUPAR and the resistivity model, any model that you're going to use, the sonic model, and see how closely those properties match the properties that you wanted to be matched. So it's just an idea of how close you are. This is a difficult problem to solve, and it's difficult because there's many solutions that are going to be valid. This cannot guarantee that everything is right, but it's going to guarantee that it's consistent, which is a lot already. And then you can see the results. In this case, which is the demo that I'm going to show in a little bit, you can see how the shale concentration was reproduced. You can see it was matched pretty closely. You have the porosity. In this case, I have both of them. Because it's a synthetic case, I have I know what the answer is, so it's a pretty good match. In the talks, we're going to see that also with field data, with some core porosity, and we're going to see that the match is pretty good. All right. Also, this slide that I like to show, I've been showing for the past 3 years or so. The way UTAPWeLS works is there's Bruce and me doing the development, then we send it out, and sometimes that's it. Hopefully, that's not it. Hopefully, there's some feedback coming back. And with that feedback, like Carlos was saying, we do the developments according to what people tell us. So here is a few examples of things that we did this year that are small but relevant developments. A little word before we go into the small but relevant. The way you talk to us, the way we get feedback is going to be very relevant for the small developments, but it's also important for the bigger developments. So if you're giving us feedback on this bigger module or whatever, the more likely that module is to be pushed up, higher up in the list, and for us to work on that. Anyway, so regarding the small but relevant, somebody wanted to see layer thickness as an earth model property, so we added it. It was easy to just generate. You can just see that. Last year we had a discussion during the workshop with Carlos and Andreas about the default composition for shale, and it used to be just elite. And the conclusion was, well, people get confused between having clay and shale because it's only having a clay mineral. So what we're going to do is we included muscovite and quartz, and it was like magic. Every time we've been explaining this module to other people, now there's no confusion between clay and shale. Now they understand we mean shale. Anyway, so that was a very small development, but actually bigger impact than you think. Another small development, people wanted to be able to see log values side by side. We did it. Somebody wanted to see, now that rock classes are becoming more relevant, somebody wanted to see rock classes as a plot. We added a plot that you can see the rock classes as a different color, easy. Another one that unfortunately Michael is not here, but this is one of his suggestions. He was having problems doing simulations for cases where you have a washout. He was getting results that he didn't think were correct. He was right. And he made a suggestion on how to modify this. And the modification ended up being 3 possibilities. Now you're going to have, for 2D simulations, you're going to have a borehole model that is going to include ideal borehole. And well, if you click on this help, it's going to give you the explanation. Ideal borehole is what we used to have, which is assume that the borehole is 4 inches thick, and the conductivity is 10,000 ohms. So we're assuming very ideal conditions. If we did that, the simulation was looking something like this. Sorry, all flat. So he was, of course, not happy with those results, and he said, "Okay, let's modify that." So we did it, and we had we did it so that it would take this into account. But the problem was the simulation, external simulation, forces the radius of borehole to be constant. So what we would give the program was a constant radius and then something like an invaded zone here. But of course that's not right, because well, it's not right, but it's what you get. And it's not right because the model, what we're giving is not what the developer was expecting. And it looked something like this, which is just very noisy and not really what you would expect. The reason is the program itself is making some corrections for the tool right at the borehole. But the borehole was not here. Of course, the results are not correct. So he suggested adding another case, which was the no correction, which would make the corrections, which would, we would have a fake, very thin borehole, and then consider these invaded zones. That would work because you have, you apply the tool corrections in that very thin borehole, and you see the actual response because of the washout, and you get these results. So this is closer to the raw data that you would get from this logging. It's interesting, and that's why I'm spending a little more time, but really making this correction took less than a day. So if you see some things like that, don't hesitate into asking us. We also, for sure, we keep talking about scripting. Scripting is everywhere. We've cleaned it up so that it's easier for you to see what is available. Something else now, we're moving into not new developments, but new applications. We have now something called the silent installation. Every year, people ask us about the cloud computing and this and that for what is the best solution for deploying the software company-wide. Now we actually talked to some of the IT people, some Wintershall, some other companies, and what they suggested was, instead of having a cloud deployment, because the cloud deployment is going to require either you guys to put your data in our server, which is probably going to be a no-no, or for us to get into your server, which is probably no-no. So the best solution was really to have a silent installation, which all it does is allow your one IT person to deploy this, the software without logging into your computer. Well, he will log into your computer, but remotely. And the key is, if you can do everything from the command window, he can do it from anywhere in the world and deploy it. Once he gets it approved for one person, it's approved for the entire company. That's what happens usually. And it saves them a lot of time. So we work with them, we develop this, and hopefully many companies are gonna use it. We know that IT is getting more and more restrictive. This hopefully solves the problem. Regarding future developments, we have we want to expand the mnemonic parameters to apply to curves selected directly from the well log set. So the visualization not only apply when you select this mnemonic, but if you say well log set gamma ray, apply the visualization that you have for that mnemonic. It's relatively small, but we want to do that. We want to have the well log editor. These two are relatively small, and we should do them within the next couple of months. We want to auto-detect bed boundaries. That's something we have in the works. It's exactly what it says. You can detect bed boundaries and apply some depth shift if you do it with multiple curves. We want to be able to automatically identify rock classes. We also have a couple of algorithms that do this already. We just need to decide which ones we're going to keep and develop the user interface. We have a linearized compositional joint inversion developed by Ali Iqbali. He's going to have a talk on this. This focuses more in the minerals. It's going to be, we're hoping to have this also this year. We keep talking about the fast 3D sonic simulator, hopefully this year. We also have, this one is also in the works, we're not too far, the inversion of radius of invasion. At some point, if you recall, we had something that could do something similar to, you could invert for radius of invasion, but it was very slow, and it was trying, we were trying to do too many things. We're now focusing on the right focus. We used to be able to, well, that module would invert for as many radius as you wanted. We're saying, no, it's only going to be piston-like, and it was just guided by the match. We're going to say, no, you need to also take into account the separation between the resistivity curves. So by having the focus in the right place, I think we're going to get a much better result. Gonzalez is working on this. Also, beyond the borehole framework, we want to be able to have, also this is another one that we've been talking about for a couple of years. Hopefully this year we really get it done. So far, everything we do is around the borehole. But we know that in some cases, you want to have some layers that are not being crossed by the borehole. We want to have a framework that allows you to do this. It doesn't sound too complicated, but it is. Well, it is. Most models are 100% Cartesian. Ours is different because we have everything focused in the well. Going back and forth between those two frameworks is not trivial. We've had a module that was able to do it. To just do it is not too difficult. To do it right, to do it so that it's actually easy for you to transfer properties, so that it's easy for you to manipulate the boundaries, that's something else. And that's what we're working on. We want it to actually be very effective and very easy to use. Also, we want to be able to transfer properties across wells regarding multi-well focus. We want to expand the multi-well QC plots so that if you have inversions in multiple wells, it's easy for you to visualize the deviations and so on in multiple wells. We want to have a module that allows you to invert for a key well database or just the database. If you have a key well with more data or the interpretation has been done a little more thoroughly, we want to be able to invert for density or spectral gamma ray response for specific minerals so that it's optimized for that field, and you can propagate that to all the wells within that field or within that formation and use it. Also parameters. All right. Now, Carlos went over this. This is our webpage. You've probably seen it. This is our email. You probably have it. We have the YouTube channel where we have the workshops. We have the webinars. I was a little surprised. I went into the old videos a couple of weeks ago, and I was surprised that some of the short-form videos that we used to do a couple of years ago have thousands or tens of thousands of views. So I think it's a lot easier for people to just watch 10 minutes videos rather than 30 or 40 minutes, and also more focused. So I think this year we're going to do a little more short form, just one for like a short video for resistivity instead of having a big video explaining you how the field case was developed and so on. We're going to just focus on usability, and hopefully we can get some more done. We have a repository for UTAPWeLS. This is just a repository in GitHub for scripting. It has a few examples for scripting. It's always easier to start doing development if you have a working example rather than starting from scratch. This is where you would do it. Now regarding outreach and training, we issued 127 licenses, which is almost twice as many as we did last year. So we're very happy that people are using it again, are using UTAPWeLS again. Hundreds of emails and video conferences. We had a webinar about a month ago on joint compositional inversion. We had that workshop. We're open again for workshops abroad. And we had two post-meeting workshops. We had one in person right after the consortium last year, where we had 11 people from 6 companies, and we had a virtual workshop with 26 people from 10 companies. And with that, I'm grateful to be here. Thank you for the sponsors. And